for format violations because they get validated. If you ever wrote exploits that are based on like fucked up file formats, if that file format is correct, then you're not exploiting anything. That is the downside, and this is what we're actually playing on here. Everything that uses obfuscation in the malware code is obviously eaten right away because, well, you can do a lot of bullshit in the instruction set. People obviously do it, but it's a clear indication that you don't want to see that type of porn. All exploits targeting the browser itself by redirecting it were patched to harmlessness. So far, we're pretty happy with the results. Of course, we have collateral damage. People tend to think that their flash files contain highly valuable intellectual property that they cannot possibly give to the entire world. Secret, if you're uploading code on a web server that is supposed to be anonymously retrieved and executed on the client side, it's no secret, no matter what you do. However, there are people that actually buy obfuscation software, and this obfuscation software obviously creates invalid code, so we drop it, except for one that's called Obfuscator that actually produces valid Swift files. And then, of course, the question is, does the porn still work? So, Fukami actually I mean, if the porn didn't work, we could have used Noscript, right? So, Fukami was nice enough to provide a very large test set. Not of porn, of flash files. So it's like 95,000 files, 45 gigs. We pushed it through the engine. 92% of the files actually validate in parsing and validation. So they're actually considered fine from a format point of view. And a sizable number, 82% actually survive the whole patching process as well and then still work. We do have an average code inflation of 224%, which is a lot and needs to get fixed. But first, performance. Because people always say, you know, it's .NET, it can't be fast, and like, why didn't you write it in C? So it's half a second to validate it and half a second to patch and rewrite it. I can wait that 1 second. But I have to admit that my machine is quite decent. If I do that on my laptop here, it would be different. So there is an obvious and a less obvious problem. The obvious problem is we're patching all the code that inflates the code massively. So the flash runs slower. I couldn't care less. However, due to this brilliant idea of having a 15-bit branch destination limit, we can actually run into the situation where we patch stuff in, and then we have a branch that would need to go over our patch, and it actually integer overflows, which we happily catch because we're running in the CLR, and we're not having to test that individually. But some flash files, especially stuff that's not coming out of Adobe's compilers, but from actual, real backends, they actually max this out quite a lot. Like the YouTube player, for example, has a number of instances where the jump would actually be not possible if it would have been 1 byte more code in the middle. So we actually need code flow analysis. Not a big surprise, you already have seen the code flow graphs. What we will introduce is jump paths in the code. So if you have a long jump, you actually split it in 2 small ones. The whole thing with this is, if they didn't have inline function declaration, I wouldn't feel bad about it. It would be a trivial algorithm. However, they do have this inline function stuff that can actually be nested as well. So we don't actually know how smart of an idea that is to patch right in the middle of a function, which is not actually going to be executed, but we're jumping in and jumping right back out. And I don't actually want to kill the AVM with that. I'm also blessed with people to work with that can, right off their asses during lunch, come up with pathetically complicated code examples where a naive approach wouldn't work. And those people pointed out this is not actually trivial. What we will also introduce to counter this code inflation is something that I call stack tracing. So we already have an object, a class representation for every single instruction. So we can actually go ahead and put the stack behavior of that instruction into that class as well. Figure out from the point of potential patching, go the way back and figure out like, what is the stack containing? Is it constants? Is it going always to the same website? Well, then we can save the patch, right? This would already be done if I weren't such a fucky coder. And you know how the train of thought is different to the real train? And because the train of thought can actually make a 90 degrees right and then go all the way into the pampa. That's what happened here. So I actually wrote a lot of code that was then later deleted. Things Blitzableiter can't do anything about yet. One is heap spraying. Obviously, you can use Flash to heap spray. If you have a browser exploit, you just put a Flash movie in that creates a shitload of interestingly colored shapes, and this color will actually be your shellcode. That is relatively trivial to do. It's pretty hard to actually tell allocations apart from legal to illegal allocations. Microsoft Research has some relatively new good work on this that we're going to check out and see if it actually makes sense in a Flash context. The Flash API overflows aren't really there yet, but we're seeing them by the metric ton in PDF now, which happens to come from the same company. And so like every third JavaScript function in PDF that accepts a string apparently doesn't like long strings. And once PDF is done, I'm expecting a lot more people to look at the same topic in in Flash. So we would need to actually check individual call arguments. That would be similar to signatures in AV, and you probably have an idea how much I like that idea. So what's the current state? Now, it isn't completely done yet, as all software ever is. We only cover the tag types that actually carry code. First of all, there were the interesting ones. Second of all, well, now there comes the task of actually writing all the code to parse glyph sets, image formats, MP3s, and stuff like that. Because otherwise the approach isn't actually worth it. We actually have to parse everything. Like the latest exploits against Flash were all with malformed JPEG content, as if JPEG was such a new thing to parse. We will need to support AVM too. I already started it. Got a bucket, puked in, and decided that we first handle AVM1 completely. But a little of the code is already there. So why do we actually go open source with this? I'd like to think of Kerckhoffs's principle from crypto to be actually applicable to most of the defense strategies that you run. Security by obscurity actually does work. I mean, ASLR is pretty much nothing else. Like, it's just very obscure where you have to return to. Other than that, it's nothing special. However, defense mechanisms that are auditable, where people can actually look into it, see how does that work, is that principle sound, are, in my world of view, preferable to big yellow boxes that somehow make you secure and someone else rich. Because usually they only fulfill the second requirement. And it's not like I'm the best coder in the world. And it's not like you want to trust my code to protect you, even from porn. Also, I want the Flash developers to be able to test their stuff. And like, if their code is like 500 times bigger than it was before, maybe you shouldn't use those dynamic data structures to find a single URL that you hard-coded somewhere else anyway. And we want to, like, this, it gets released as a library, so people can actually integrate it into Firefox, into Squid running on Mono or whatever, or even make it a WordPress plugin. We don't really care. So,